Hi everybody! So today we're going to take a look at a corundum sphere that displays asterism. Asterism is a star-shaped pattern of light that often results from the scattering of light by inclusions in a crystal. And these inclusions are going to be crystallographically controlled, so our asterism actually gives us yet another way to link together our optics and crystallography for corundum. Let's take a look at one of these spheres. These are synthetic corundum spheres, and they're about 8 millimeters in diameter. These are a deep red color, and so we can also refer to these as ruby. A ruby that displays asterism is also known as a star ruby, and this nomenclature holds for other species as well. Quartz that displays asterism is known as star quartz, and garnet that displays asterism can be known as star garnet. So today, instead of saying red corundum sphere that displays asterism, I'll probably just say star ruby. And the star ruby that we're examining today is indeed synthetic. If it weren't and were natural, it would be very, very expensive. But that isn't the case here, and you can pick up your own synthetic corundum sphere with asterism from the eBay store Snellius Minerals if you'd like to follow along with our experiments today. You'll also want some form of polariscope and also a normal everyday flashlight. Corundum has been featured in many of our educational videos, so today we'll do a little bit of background on corundum, but if you want a deeper dive into corundum, you should check out Optical Mineralogy Big Picture. So, our minerals are defined by their chemistry and structure. This in turn determines the crystallography that we'll see in a macroscopic crystal as well as the optical properties of our mineral. The chemistry of our corundum consists of aluminum oxide, Al2O3, and the structure of our corundum consists of oxygen in a hexagonally closest packed arrangement with 2/3 of the octahedral interstices in that arrangement containing aluminum. In the video Optical Mineralogy Big Picture, we go and make a marble structure model for our corundum, which you can see here. This helps us to investigate the space group symmetry that's going on at the micro scale in our corundum. In that video, we also examined macroscopic corundum crystals and the point group symmetry of corundum and how this relates to our space group symmetry. And the Optical Mineralogy Big Picture video finishes by taking a look at the optical properties of our corundum and how they're related to those symmetry elements that we've talked about. We can summarize the relationship between our optical properties and our crystallographic axes by taking a look at the optical indicatrix for corundum, a three-dimensional representation of the refractive indices of our corundum. For corundum and any other uniaxial mineral, our c-crystallographic axis is also going to be our optic axis. And when using a polariscope, we'll be able to generate a uniaxial optic axis interference figure in this direction for our corundum. That'll be important for us today. Now let's take a look at our corundum sphere that displays asterism, our star ruby. We are viewing our star ruby with transmitted plane polarized light in our polariscope. And as we rotate the sphere around a bit, you'll notice some pleochroism as we change from lighter to darker red. However, there's a much better, more in-depth video about the optical properties of our corundum sphere that you should check out if you want to understand more of what's going on here. That's Snellius Minerals LLC, corundum sphere. Since we've seen some pleochroism, we know that we're not looking down the optic axis of our corundum sphere, and the easiest way to actually find that optic axis is going to be bringing in our upper polarizer and taking a look at our sphere with cross polarizers. And here, as we reorient our sphere, we can see our uniaxial optic axis interference figure. For many of our other samples, we'd need to bring in a converging lens in order to generate an optic axis interference figure, but in this case our spherical corundum is already acting as a converging lens, and so we don't actually need one. Now that we've found the optic axis of our corundum, we know that we're also looking along the c-crystallographic axis of our corundum as well. Now, we haven't really done anything different from what we've done in our corundum sphere video in the past, but now it's time for our star ruby to shine. What I'm going to do here is keep our star ruby from changing orientation, get rid of our polariscope setup, and then shine a flashlight on our star ruby so that light reflects back into our camera. What we're seeing here is a display of asterism. In this case, our star ruby has a 6-rayed star, and this is fairly standard for star ruby given the symmetry of our corundum. Different mineral species can display stars with different numbers of rays, and this is often related to the symmetry of the mineral that we're looking at. Using our polariscope earlier, we oriented our star ruby so that we were looking down the optic axis and c-crystallographic axis of our star ruby. Now I want you to think about how the pattern of our asterism is related to that crystallographic orientation. And we'll explore this by rotating our star ruby around. Note that the pattern of scattered light that we see varies as we rotate our star ruby into different orientations. And this is because that pattern is determined by crystallographically oriented inclusions in our star ruby. And in the case of our synthetic star ruby, these are likely oriented needles of rutile, a titanium oxide mineral that has been purposefully exsolved from corundum in order to generate the pattern of asterism that we see. There are actually patents for this process going all the way back to 1949, and here's a reference to that patent, along with a paper that discusses the cause of asterism in star corundum if you'd like to explore further. There is a whole bunch more literature on this topic, but for today we're just going to try and keep things very simple. We'll go back out to a view of our star ruby displaying asterism, and the reason we see these scattered bands of light that make up our asterism is because of an oriented network of needle-like inclusions in our corundum, in this case likely rutile needles. These needles occur perpendicular to the bands of light that we see making up our asterism. Although you can't see these needles in this specimen, here's a representation of how they're oriented with respect to our star. And the orientation of these needles is in turn controlled by the crystal structure of our corundum and how they exsolve from corundum at high temperature. Our network of needles ends up being perpendicular to our crystallographic axes. Here's a photomicrograph of these needles in a natural sapphire sample. And thanks to Elise Skalwold for letting me use her photomicrograph. Let's try and tie all these concepts together now. The asterism in our star ruby ultimately gives us crystallographic information about the orientation of our corundum because the pattern that we see is derived from crystallographically controlled needles in that corundum structure. So even though our star ruby no longer has any crystallographic forms associated with it, we can still understand its orientation. Our synthetic star ruby sphere also allows us to examine the optics of our corundum, and we can see how our crystallography and optical properties relate to one another. If you're interested in trying out these experiments for yourself, you can pick up the corundum sphere with asterism at the eBay store Snellius Minerals. And if you have any questions, comments, or concerns, you can reach me by email at snelliusminerals@gmail.com. Here are the references for the video today, and there's a whole bunch more out there on asterism if you'd like to dig a bit deeper yourself. Thanks again for watching, and have a great day.